So we're doing lesson 9.1e. This is the last one for all of these radical little mini units that we've been doing. And we're going to simplify radical expressions that involve conjugates. The rest of it will also be just a little bit of review over cubics and that kind of thing. So here's a dilemma. All of the problems that you had over the last few days where you had to rationalize that denominator, all those denominators only had a single term. It had just one term. It could be just a radical. Sometimes it was like a coefficient in a radical, like 2 square root of 5, but it was still a one term. It wasn't multiple terms added or subtracted, okay? So it wasn't that big a deal. We figured out that we just needed to create a perfect square or create a perfect cube, like number, what was it that you asked about, 42, right? The cubic, right? We said, oh, we got to multiply by that cube root of 2, and that'll give us a perfect cube. That'll solve the problem of having the radical on the denominator. Good to go, right? But today, we kind of take it one step further, and we learn how to deal with a denominator that has a sum or difference, right? You've got now essentially what we used to call a binomial in the polynomials, right? We've got two terms that are either added or subtracted, and one of them or both maybe have a radical, okay? When that happens, it's not quite as simple as just multiplying by that root. And let me show you what I mean by, let me show you what I mean by that. Let's pretend for just a moment, I'm going to keep it pretty simple here as just a random example, that I've got this right here, 1 over 2 plus square root of 3. And I need to get rid of that square root of 3, right? If we try to just handle this the way that we did last week, and we're like, oh, well, I'll just multiply by another square root of 3 because I know that's going to give me square root of 9, right? So if we try to do that, check out what happens, right? I decide, well, I'm just going to do it times itself because that gives me a perfect square. Well, it will. That's true. And it will get rid of that radical. The problem is that I'm going to now be forced, to be mathematically accurate, to do this correctly. I would be doing all of this times that. And that would involve me having to distribute this if I'm doing this correctly. And so, yes, square root of 3 times square root of 3 is going to be square root of 9, which is just a whole number 3. And that radical is going to go away. However, in my first term, I'm going to end up with 2 times what? Square root of 3, right? And so I pretty much just end up with a radical still just in the other term, right? And I really didn't go anywhere. I just kind of went around in a circle, and I'm back at the same dilemma. And I always think it's like this is kind of like that game whack-a-mole, right? You get one, and the other ones come up, and you get, no matter how many you try, you can't get them all, right? So there's got to be a different way to fix this issue. Luckily, there is, and it's something you already know, so it's not really anything necessarily very new, okay? Remember, our goal, what gets rid of our radicals every time? The perfect squares or the perfect cubes, right? So there's this little thing that we've been talking about for several weeks now, the difference of squares. That right there will guarantee me a perfect square in both of my terms. And we've done difference of squares before, okay? We know that when we multiply the same two numbers, added and subtracted, what you now will know are called conjugates, right? We talked a lot about difference of squares. We didn't really talk a lot about the word conjugates, but difference of squares, these two binomials, they're conjugates of each other, okay? These are conjugates right here. So that's just a fancy word for saying, hey, the two terms, or binomials, or the two sums or differences, they're the same numbers, just one is added, one is subtracted, okay? And when we do that, we've worked with this before. We know that the result is just a perfect square minus another perfect square, okay? That's going to guarantee no radicals for us, okay? So that's what we're going to use. We're going to use conjugates. And again, conjugates are just the same two terms, but some are different, the opposite. So if you started off with a sum, you're going to use a difference as your conjugate. If you started off with a difference, you would use a sum. You would just use the one that's the opposite, okay? So I'm going to go through and review really quickly why a difference of square is what it is, and then we can use a shortcut for it. That's how we're going to solve problems like this example and the rest of them on your notes, okay? So just a quick review, right? If you just need a little refresher, what's really happening is we're still foiling or doing a 2x2 box, but when that happens, look at that, and you happen to have conjugates, right? Look at what happens. When we do our first two terms together, they're the same term. So negative 7, sorry, not negative. Square root of 7 times square root of 7 is square root of 49, okay? So there's one of our perfect squares achieved, okay? Because our first two terms were identical. So in that first part of FOIL, it's something times itself. That's already good news. But then, when we do the outer terms, it's square root of 7 times square root of 3. We can do that, but it's going to give us the square root of 7 times 3, which is 21. Now, that's not looking really great. But just wait, okay, to see what's going to happen next. Okay, so we got square root of 21 there. Then we do the inner terms. Well, the inner terms is a negative square root of 3 times square root of 7. What does that result in? A negative, what? Square root of 21. And we have like radicals right there in the center. But not just like radicals, they're opposite signs, right? And what do you think is going to happen to those middle terms? They're going to cancel out. Does this sound familiar? Yes, we did this with polynomials, right? Same idea. So those two middle terms, instead of doubling up like the perfect square stuff, they cancel each other out. Okay, so there's no middle term. Okay, and then the last term is a negative times a positive, which always gives us a negative, hence the difference. It's always a difference of two things, right? So it's a negative, and then square root of 3 times square root of 3. Well, that's a perfect square. It's square root of 9, right? And so we all just agreed a moment ago, the two middle terms cancel, and our result always ends up being just that first perfect square we had, square root of 49, which we know is what? 7 minus, and then that other perfect square, which we now know square root of 9 is 3. And guess what? We do not have any longer. No radicals. Okay? It's just 7 minus 3, which is 4. A nice whole number 4 with no radicals involved. Okay? That was all review, and you certainly don't have to show that every time. I just wanted you to see and remember, oh yeah, that's why that works. That's why that thing is what it is. But the shortcut to that is just knowing this direct relationship for difference of squares, knowing that pattern. So when we see it, or when we create our own conjugate, as soon as we see it, we know, oh yeah, since those two are conjugates, like number 2 here, my result is just going to be the square of the first term minus the square of the second term. Okay, so you can just jump right to that. And the square root of 10 squared is what? Just 10. And the square root of 6 squared is just 6. And there it is. And 10 minus 6 is 4. Okay, so it fixes the issue. That's what we're going to be using. Okay, so you rationalize the denominator by multiplying by the conjugate. If you already had a difference, you're going to create a conjugate sum. If you already had a sum, you'll use a difference, but you'll just make sure that they're opposites so this pattern comes into play. That's it. Okay, so let's try like number 3, sorry. Okay, so it says simplify the expression. We can kind of look around and make sure there's nothing like, stuff that can be reduced or perfect squares in the radical, but I think we're ready to roll here, right? Really, all we have to do here, or all that's left to do, is get rid of that square root of 2. So we're going to have to use this concept of conjugates because we have a sum or difference here in the denominator. Okay, so I'm going to use a conjugate. So what's a conjugate to 5 minus square root of 2? 5 plus square root of 2, right? So that's what I'm going to use on top and bottom. Okay, if I do it on the top, if I do it on the bottom, I also have to do it on the top. So this is what I'm going to multiply my numerator and my denominator by. Okay, that's the conjugate of my denominator. All right? Okay. Now on the top, I'm doing 1 times all that, but multiplying by a 1 doesn't really make any big changes. So that just stays 5 plus square root of 2 in the numerator. However, in the denominator, the whole point of doing that is that I know my result now will just be the square of the first term. So what's our first term, guys? 5. So it's going to be the square of 5 minus the square of the second term, which is the square root of 2, the square of that. Right? So I know that in the denominator, I'm just going to get the first term squared minus the second term squared, which is what I just wrote. Okay? And then we just clean that up, right? So Again, not much to see up at the top here, at least right now. But in the denominator, 5 squared is 25 minus, and then what happens here if I have the square root of 2 squared? That's just 2, right? Yeah. And I've cleared my radical from the denominator. Mission accomplished. Now I just have to say, what's 25 minus 2? 23. So our solution, or our simplified version here, is 5 plus the square root of 2 over 23. And I check to make sure there's nothing in common. We're good. That's our answer. Okay? That's using conjugates to rationalize the denominator. And you're really using a conjugate to create a difference of squares. Okay? Where I can guarantee myself just perfect squares and nothing else. Okay? Let's try number 4. So nothing here to simplify other than getting rid of the radical in the denominator. What would be the conjugate to 4 minus square root of 5? 4 plus square root of 5, right? But if I do that on the denominator, I also have to make sure I do it to the numerator. It's got to be the same on top and bottom. So there it is. Okay. Now this time around, I do need to distribute that 3, and that's more than 1. So I definitely need to actually multiply that out. So in the top, I'm doing 3 times all of that. Okay. So 3 times 4, those are both whole numbers. They're compatible. I can do that. 3 times 4 is 12. Right? And then for the next one, 3 times the square root of 5, those are not compatible. I can't actually multiply them. I'm just going to leave them next to each other. Okay? So I'm going to just do 3 square root of 5. That's my numerator. Everybody okay with that? I just distributed the 3. And in my denominator, I know that all I have to do is do the difference of perfect squares. So my first term will be the first term squared minus, and then square root of 5 squared. Okay? And then let's clean that up. 4 squared is what, guys? 16 minus, and then the square root of 5 squared is just 5. So our final answer is 12 plus 3 square root of 5 over 11. And then that doesn't really simplify any further. We're good. How are we feeling about these? Pretty good? Okay. All right. Try number 5 on your own, if you will. Okay. See how that goes. Number 6 is a little bit more complex, but once you try 5, it feels really good. Then you can shoot for 6 as well. For number 5, do you guys agree our conjugate here would be 4 plus square root of 3? Is that okay with everybody? So 4 plus the square root of 3. Okay. In the numerator, we're going to need to distribute that square root of 6 to both of those. So that's going to give me 4 square root of 6 plus, and then here, 6 times 3, those are both radicals, so I can and should multiply them. I get square root of 18 there. So put a pin on that, because what do y'all think? Is that simplified? So you want to keep that in mind, right? And then for our denominator, that part, we're getting the hang of it now, right? Difference of squares. So it's going to be the square of this first term minus the square of the second term. Okay? And then we clean this up. What goes into 18 that is a perfect square? 9 and 2, right? So we got to keep an eye on that, catch it, and make sure we take care of that. It all needs to be simplified. So I'm going to rewrite that square root of 18 as 9 times 2. In my denominator, I know I'm going to do the 4 squared minus, and then square root of 3 squared is just 3. Okay? And then I'll take care of this last part. Still can't do anything with the 4 square root of 6, but that square root of 9 times square root of 2 is just 3 square root of 2. And down here, I just get 13. Okay? And that's as far as we can go. There's nothing else that can be simplified there. So are we okay with those? Is that okay? Yeah? All right. Turn it over. If y'all feel good about that one, let's turn it over and let's actually do, which one do I want to do with you guys? I want y'all to try number 8. And then if you feel good about 8, we'll go to 9. 9 is the one that I really want to make sure we discuss because it brings up a little bit of reminder about simplifying. So try number 8. Over here. So let's try that. Let you guys work it out. We got our conjugate here would be square root of 3 minus square root of 5. Square root of 3 minus square root. Okay, and this will have to distribute. So because there are all radicals, I actually can do all that multiplication. This will be square root of 15 in the first term, and then square root of 25 in the second term. Does that simplify? Yeah, right, that's a perfect square, so we'll be able to clean that up. That'll be nice. In the bottom, I know I'm getting the square root of the 3 squared minus the square root of the 5 squared. Okay, so then we clean that. We get square root of 15 is still there, but this is just a whole number, 5 though, minus 5. On the bottom, I'm just going to get 3 minus 5. And that simplifies to just a 2 or a negative 2. So I'm going to put that negative out in front. It's not good to leave that in the denominator. It makes it harder to read. So I'm going to just put a negative out in front and then just read that. Negative square root of 15 over, minus 5 over 2. Okay? Give me some thumbs up or down. How do we feel? Yes? Great question. Are you talking about right in here? Okay, that's a really good question. I can't, and here's why. It's tempting, right? They look like, well, you have exactly the same thing on top and bottom. The reason I cannot simplify those 5s is because they're not factors of that numerator or denominator. They're being added or subtracted, but they're not a factor that necessarily goes in evenly. So I always give the example. To give you an example of what I mean, right? I always give this example. Think of that as, for example, being 3 over 13, right? What do y'all think? Can I simplify 3 over 13? No, right? But what I have right here is like as if I wrote 3 over 13 as maybe 3 over 10 plus 3, right? Because it's addition or subtraction. Just because I see it doesn't mean it's actually a factor that goes in evenly. And that's all I can simplify. So that's a really good point. That came up in both earlier classes. But just like I can't just cross out these 3's just because I see a 3 on top and bottom, because 3 is not a factor of 13. It has to be something that is a factor being multiplied, okay? Which is going to come up. That's why I want y'all to put a pause on it on 9, because that is going to come up, but I'll show you what that looks like, okay? I can't do it like this when it's just one, 2 things there if it's addition or subtraction. So that's as far as we can go on number 8, okay? But check out number 9. So this is the one I really want us to focus on. So listen up, right? This is a little different. Quickly sign up. Okay, so on number 9, we've got 5 over negative 3 minus 3 square root of 3. Okay, let's talk about that conjugate. What would that be? What would be our conjugate here? Negative 3 plus 3 square root of 3. All right, so just the opposite operation there in the middle. So this is going to be our conjugate that we're going to multiply top and bottom by. Okay, and then we're going to multiply by that 5 on the numerator. So that's going to give us a negative 15 plus 15 square root of 3. In the denominator, I know I'm going to get the square of this term here, the negative 3, minus the square of the 3 square root of 3. Okay? Square of that, sorry. Notice this, there's a reason why the whole time that I've been doing these, I've been putting those in parentheses. Okay, and this is why, because once you start having things with whole numbers and radicals, you got to remember the whole term is being squared. So that's both the 3 and the square root of 3. The whole thing gets multiplied by itself. So it's 3 square root of 3 times 3 square root of 3. So keep that in mind. Okay. All right. Not much to do with the numerator so far, but let's clean this up down here. Negative 3 squared is just what, guys? 9 minus, and then 3, when I square this, I'm squaring both things. So 3 squared is 9, and then the square root of 3 squared is just 3. Okay? And then 9 times 3 is 27, right? So we end up here, just so you know where that came from, we end up with 9 minus 27, which is going to be negative what? 18. Now, really relevant to the question that was just asked a couple minutes ago, here you can look and see that there is a common factor that can be reduced, but it's because it goes into all 3 of these terms. So we really have 3 terms here. We've got the 2 numerator values here, the negative 15 and the positive 15 square root of 3, and then we have 18. What goes into all 3 of these? 3. Because it's a factor in all 3 terms, yes, you can and should and need to simplify that out, okay? So I need to notice, hey, wait a minute, there's a 3, and in fact, with all these negatives, especially when my denominator is negative, it's smart to just pull a negative 3. That way you get rid of some of that negative stuff. So I can factor out a negative 3 from my numerator, and that would leave me with 5 minus 5 square root of 3. And then, of course, I know negative 18 is the product of negative 3 times 6. So there's this negative 3 that is a common factor in all of these terms that I can and need to reduce by. Okay, so the final and best answer here is 5 minus 5 square root of 3 over 6. And this is how I know that's really, really simplified, because all 3 of these don't have anything in common among all 3 of them. Okay, that's kind of what we were checking for. And all of these 5, 1, and 23, those don't have anything in common. 12, 3, 11, those don't have anything in common. So we were okay, but that's what we're looking for each time. Okay, so try number 10. Okay, similar type of problem. Try number 10. Okay. Give you guys a head start. Check your work. Make sure you use the correct conjugate. And start with that. So your conjugate should be 4 minus 4 square root of 5. Okay. Then we distribute. You get 12 minus 12 square root of 5. On the bottom, we're going to get the first term squared minus the second term squared. But when we do that, we know this comes out to 16 minus, and then this comes out to 16 times 5. Is that okay with everybody? This 4 squared is 16, and square root of 5 squared is just 5, and those two things are being multiplied together. So when we square that, we get 16 times 5. What is 16 times 5? 80, right? So then this gives us an 80 here, so then we're doing 16 minus 80. So really, our new denominator, guys, is negative 64. Okay? So when you evaluate that denominator, if you use the conjugate and you did the difference of squares correctly, you should get a negative 64. And then comes the next question, right? As we're checking, do all 3 of these have something in common that we could factor by further? Yeah, what goes into 12 and 64? 4, right? And in fact, since my denominator is a negative, I'm going to go out and actually say, let's pull a negative 64. I'm sorry, a negative 4, I apologize, yes. That leaves us a negative 3 here and a positive 3 square root of 5. In the denominator, I can split this as negative 4 times 16, and then I can reduce by that negative 4. So our simplified version, when it's all said and done, is negative 3 plus 3 square root of 5 over 16. There it is. Okay? Any questions? Are y'all good? Okay. Then this last one, I'm just going to do one of these unless y'all want to see both. This is just reviewing the cube root stuff from last Friday. Okay? It's not really have to do with conjugates. It's just reviewing and jogging our memory on cubic roots. These are all cube roots, so I can distribute this in. So let's try number 11. Okay, I can distribute that in. And because they're radical with radical, they're compatible, right? We can actually multiply that. So in this first one, I get the cube root of, what's 2 times 108? 216. Good, yeah. 216. And then minus, and then when I do this next one, it'll be the cube root of 2 times 135, which is 270. Excellent. And then the question is that simplified fully, or can we go further? So let's ask ourselves that. Is 216 a perfect cube? Yes, good. We're starting to get the hang of those, right? So 216 is a perfect cube. What's the cube root? Just 6. Good. So this just gives me 6. This completely simplifies. That first part totally simplifies. However, 270 is not a perfect cube, but what perfect cube goes into 270? You can kind of already see it there in the number. What do you think? 27. 27 times what? 10, right? So I can break this up into 27 times 10, because I know 27 is a perfect cube, okay? In fact, what's the cube root of 27? It's 3. So this part becomes a whole number 3, but that other 10 stays in as a cube root. And then that's it. That's as far as we can go, because we don't have like radicals or anything, and that's our answer. Okay? Just a little review there. What's that? So 27, no, because when you take, so 3 times 3 times 3 is what gives us 27. So the cube root of that is 3. Yeah, we're not squaring it this time, okay? It's a perfect cube, not a perfect square. Alrighty, give me some thumbs up, down, how do we feel? All right, are we good? Huh? Yeah, let's do 13, and we'll finish off with that one. Okay, so the first thing about 13 is that I don't want, and on the quiz, I won't want this to the nearest meter. Okay, let's do simplified radical. Okay, so first of all, it tells us that the ratio of the length to the width of a golden rectangle is that ratio right there. Now, we know usually ratios can be shown either with a little dot, the little colon, the word to, T-O, or by division, comparison by division, which is what we're going to use here so we can set up a proportion. Okay. So we know that the ratio of length to width is 1 plus square root of 5 over 2. Okay, that's the length to width ratio. Okay, the length of a golden rectangle is 62 meters. So one set example is 62. We want to find the width. So we're setting up a proportion here that is comparing length to width, length to width. Okay, and then how do we solve once we set up a proportion? How do we solve it? Cross multiply, right? So we're going to do the cross product. So that means that W times that 1 plus square root of 5 has to equal the product of the other two, which is 62 times 2. That gives us 124. And then what would I do here to get W by itself? Divide by, right? So if they're multiplying that by W, to get rid of it, we then divide it. So now I'm dividing by 1 plus the square root of 5. That gets rid of all of that. So W is going to equal whatever that 124 over 1 plus square root of 5 is. But that's not simplified, right? This is our answer, but we need to make sure we leave it simplified, so then we use the conjugate to do that. So the conjugate of 1 plus square root of 5 is 1 minus the square root of 5. Okay? So on the top, that means 124 minus 124 square root of 5 when I distribute. On the bottom, it just means 1 squared minus square root of 5 squared. Okay? Now let's bring that up. So, again, on the top, this is my numerator. On the bottom, 1 squared is just 1. And the square root of 5 squared is just 5. And what's 1 minus 5? What? Well, oh, yeah. Well, we're getting there. So anyway, so then, yeah. Don't forget to get rid of the negative. Yeah, get rid of the negative. Square root of 5 over negative 4. And then there's something in common here. You pull that GCF, and you're all set. So then it's just a matter of pulling that negative 4 GCF out of all of those. So square root of 5, and then on the bottom was that another negative 4. These guys cancel. So our width is negative 31 plus 31 square root of 5, and that is in meters. Measure width.